Well, thank you, Rahul, for a great introduction. So last time I visited UIB was 1994. Looks like half of this room was not born then. Yeah, and maybe half of behind that room. So we have a very long standing work together. Rahul mentioned that we started as postdoc with Jim Gunton together. And then Thomas first visited Kansas State, and then Joanne visited a few years after for several papers together. And then I was doing various things, and then in between, for 12 years, I decided to visit the dark side of the universe. So I was department head for 6 years and dean for 6 years of the whole college. Our college has 26 departments. And after that, I came back to physics and I wanted to do something very different. So I'm back here. Okay, all right. So the talk I'm going to give today, you saw the title, and the point I was trying to make by the title is that sometimes in physics, we have a subject that we say, okay, we know everything about it, the chapter is closed. And there are still a lot of surprises hidden even in that subject that we say we know everything. We don't. We don't. Actually, the first time this happened is probably in late 19th century. And right after Maxwell's success, it was declared that we know everything about physics. Time is now to just go calculate. And then there are some experiments that were done on black body radiation, and you know the rest of the history. So let me start with that. So initially, in the 1970s, late 70s and 80s, there was a lot of work on this so-called fractal aggregates. It excited a lot of statistical physicists. And mainly what happened is that there are two kinds of what did I do? This one. Yeah. So the two kinds of aggregates that folks studied then, one is called a diffusion limited aggregate, and the other one is diffusion limited cluster aggregate. So here you'll have one cluster, you put a seed in the one particle in the middle of your system, and then you release another particle far away, and it diffuses, comes next to it, and once it's within certain distance, it gets attached to, and it cannot move anymore. So now your cluster has two particles. Then you release another one, and it comes and it hits one of the two, and then become a member of the cluster. And the cluster grows like that. So those are your DLA cluster. And the DLCA is that you start with some large number of monomers, not one, and then they move around, and then they find a friend. They become a dimer, two particles, and then that can move around, meet other people, other particle, and become a member of that cluster. And the clusters themselves can come together and create new clusters. So these are cluster aggregation. And this is just one cluster. DLA is one cluster. These are many clusters. And so how then the shape of the cluster evolve with time, and the kinetics of cluster aggregation. That's what people have looked at. Several people in the 70s and 80s, they worked on that, and they wrote a review, they wrote a book. And when a book is written, you say that, okay, that chapter is closed, we know. And so the morphology of that, these both type of clusters are fractals. And so the number of particles there is given by the linear size, Rg we call it, and the fractal dimension, which is less than the special dimension. So that's why they are called fractals. So Okay, this will take me to the next. So this is a typical DLA aggregate. So here was your first seed, and you released a particle that came next to it, and then it grows like that. Since you are releasing particle far away, its probability of being caught by someone outside is very large, as you can see, and that's why it creates this kind of open structure. Very rarely a particle will come to the middle. They'll be captured even before that. There are all these sites. So that's how this cluster grows. And here is this is an example from experiment. So this is what happens. Actually, my mother invented this, but she didn't know that. It's in her kitchen. She had all these soot particles, and they created this aggregation, but no one told her that these are actually something good. She immediately cleaned them as they are forming. Now, more mystery to it later. So I'll come to that later. So here in a soot, if you burn something, a hydrocarbon gas that doesn't burn completely, it'll create soot, and then the soot particle will come together and they will form this kind of cluster. So this is from experiment. This is the length scale. You can see 1 micrometer, 1 micron, and they form this. These are DLC, cluster aggregation. If you wait longer, these clusters will come together and they will create a bigger cluster. So that was the state, and my colleague at Kansas State, Chris Sorensen, has been doing experiment on that for a long time. Then, okay, so this will be a typical way to describe it, is that this is your cluster, and now you draw the sphere around it, and you define a radius of gyration. You guys know what that is. And this will be 2a will be the size of this monomer. So a is the radius of this monomer. So this is a typical cluster that shows up in a cluster aggregation. Then, so this was happening in late 70s to early 80s, and things were kind of closed. And then this can be described by mean field models. These models actually, as you can see, are done in 1916. And you say, you create a mean field model. You say that, okay, this will be independent of what the clusters are. And that's the typical description of mean field. They'll come together with some probability. A cluster of I and J will meet, and then it can a cluster of the first part will be that a cluster of I minus J and J can meet, and then I and J can meet together to create a cluster of I. These are the two ways that a cluster of I can be created. So you write that down. And then you can simplify this kind of model by saying that, well, the most dominant kind of aggregation will come from equal size. So you say that, okay, it will be equal size. So this becomes now K and K. And you write down a very simple equation. You can solve that. And then you can also define a kind of a homogeneity of this kernel, if you will. And you define this quantity lambda. And the kinetic exponent, so that the number of cluster growing as t to the z, for example, that is related to this lambda. And z is 1 over 1 minus lambda. And people found that for DLC aggregates, lambda is 0, and so clusters will grow linearly with time. So this was, 70s and 80s. And then in 98 or so, Chris Sorensen did some experiment, and so you can see that here will be your the soot clusters that I showed you at some early time, and then they become this larger in size. They come together, and then finally they will come together and span the whole system. So they are actually forming a kind of a gel. The example of gel that you might have is in your Jello. The Jello is something that spans from one side of the system to the other. typically gelatin molecule, a very low volume fraction you put in the water, and they create fractal cluster and spans and holds the water in them. That's your typical jello. So this is your aerosol gel. So this is gelation in aerosol, which was new. And so I was very interested immediately when I learned about this experiment, and also that the kinetics speeds up as the system becomes dense. The kinetics speeds up. So now you can look at the morphology also. You can see that there are actually two parts to the morphology. One is this 1.8. So what happens there is that you are looking at a smaller length scale, and this is what the typical DLCA clusters are. They are 1.8 fractal dimensions. But if you look at smaller QS, larger length scale, then you are looking at a fractal dimension which is much larger, 2.6, than 1.8, the traditional thing that folks have studied in 70s and 80s. They kind of stopped here, 1.8. Turns out that there is a difference between, look at the cluster here. This is 0.72 micrometer and this is 9.5 micrometer. If you look at there, it's more open. So 1.8 fractal dimension makes kind of sense. But here is more denser, and 2.6 fractal dimension typically shows up in percolation. And we're seeing that kind of effect also, that the whole system spans from one side to the other. So they are percolating. The question is, okay, so we have the same fractal dimension, but how does it get to that percolation limit? So that's what interested us. Oh, there is another part to it that you can see. This is a transmission electron microscope study. And you can see that if you zoom in, you will find very open network, which has a fractal dimension of 1.8. But over a larger scale, then it becomes more denser and it has a different fractal dimension. That was showing up in the light scattering data also, which is zoom out, choose a different Q value, and you find a slope of 2.5. Choose another one, then you find a slope of 1.8, the traditional DLCA cluster fractal dimension. And they also found that which one is Z? So this is the kinetic exponent. You expect to be 1, and you do start with 1, but as the system volume fraction increases, then you see that this becomes larger from 1 to first about 1.2, and then it goes to 1.6, 1.8. It's hard to do experiments beyond that because it happens very fast. But this is where simulation comes in, and we show that it actually goes beyond that. So these two new questions come in. But for a field that was declared to be all known, there is no future in it, that all of a sudden, almost 20 years later, pose two new problems, new questions for us. One is that, what is this faster kinetics coming from? And second is that, how can we develop a comprehensive model? Not just saying, oh, it's percolating, oh, this is DLCA. How do you describe the whole path starting from dilute clusters into gel? So those are the two new problems that came our way. And here is some computer simulations data. And so you can say that this side is cluster size, left-hand side. Ignore what is written there. And this is time t. Of course, time is in some sort of simulation time scale.
It's DLCA.
Yeah, this is DLCA simulation. And so, yes, and you see that most of the previous work was done on very small dilute volume fraction of about 10 to the minus 4 to 10 to the minus 3. And here you will find that is linear. But if you increase the volume fraction, system is dense, then it starts out that, then it becomes larger, and then the kinetic becomes much faster, which was not known 20 years before that. Now, the question that I'm going to address next is, what do we mean by the system becoming dense? So that's what we are going to look at. So the question now is, why then a dispersed system, why is it going to form a gel? So if this is unstable, then if you're in a gelatin solution, then the gelatin molecule, part of it will attract another molecule when they find it and get stuck to it. If you have a different kind of a colloid, you may have to trigger something by adding salt or something to screen their electrostatic repulsion so that particles will come together. So if you make something unstable, the aggregation will occur and cluster will grow. Now, if the cluster fractal dimension d is less than the space dimension, so that will happen every time that the cluster is not totally compact. So if not like a two water drop comes together and surface tension will make a bigger drop, then the dimension of these drops stays as the special dimension. But anytime a fractal aggregate forms, this dimension will be less than d, and as a result, the clusters will try to grow and fill the space, and then that's how they will span. Okay, so here is an example. So what matters is that is the two length scale that one need to worry about in this problem. One length scale is the radius of gyration. That's the size of the cluster, mean cluster, and that will grow if we increase the cluster size. That will grow as 1 over the fractal dimension. So it grows like that. This is your straight line. And the other one is the distance, the nearest neighbor distance between two clusters. And that will grow 1 over the spatial dimension d. So if d and big D are different, then at some point they will meet here. And before that, you can call it this part when Rg and Rnn is widely separated, then you can call that a dilute phase. In between, when they're kind of comparable, then you can call it a cluster dense phase. And then finally, they will come and meet at one point, what we defined as the ideal gel point. Why is it ideal? Because we do a lot of scaling analysis to come to that point. But usually what happens in real life is that the clusters also have finger-like surface structure and all that. So the real thing could be a little different from that. So here it is. The aggregate size goes as 1 over df. If df is 1.8, that's size to the power 0.56. And the mean separation is 1 over 3, which is 0.33. And then the system will gel. So we have written a review on that. Okay, so here you see something here is that now we are starting out with a volume fraction of 0.001, and for our simulation time, this remains linear growth, and it does not show any deviation from maybe towards the very end, but then we are also having finite size effect. But if we increase the volume fraction a little bit, then you see that it goes linear first and then speeds up. This is your ideal gel point. And the ideal gel point depends on the volume fraction you're starting out with. So if the ideal gel point is very low, then the linear part remains for a little while and the kinetics speeds up. So you can span the whole thing in the simulation, which is hard to do in experiment. So over one part, when this becomes very, very dense, the exponent becomes 2.2. So you can do some part of the simulation. You can see that starts with z, increases in between, but finally it goes to 2.2. So how do you figure out this exponent of 2.2? So we did some scaling analysis to figure out exponents in at various regimes. So I'm going to quickly go over that, not spending a lot of time. So mainly what happens is that two parts to the scaling analysis. One part is that this kernel K that drives the kinetics, you can write that as size to the power lambda, which lambda is the homogeneity exponent, which for DLC is 0. And you can also write that as two parts. One is that the velocity of the cluster times the cross section of the cluster. Those are the two things. How quickly the two clusters coming together and what is the cross section for them to connect to each other. Those are the two things will dictate your aggregation. So we write that and then we try to estimate this. So here's a simple case where we are estimating things moving around in a very, very dilute atmosphere in Mars, dust particle in Mars. Okay, what happens there? Well, most of them are moving like, the RMS velocity of these clusters will be given by kinetic theory, 3 kT over m, and m should be related to the size of the clusters. And so in this case, the cluster velocity should go as 1 over square root of m or n. And the collision then going to be proportional to the radius square, rg square, and then you can write that as 2 over df. So you put it together and you put down the fractal dimension for this ballistic case that is known from other studies, and you find z to be 2.2. So what's happening is that, this is very curious, is that the particle when the clusters are starting in the dilute phase, they are diffusing and coming together. But when they are very dense and big, they don't have much room to diffuse. So in between, they're moving like in a ballistic particle in a straight line. And so the kinetics becomes different. And we can estimate that. Then we can also do the diffusion case, that in the dilute case, you can say that Rg is the only relevant length scale. Why is that? Because if a dilute case, you have one cluster and other clusters are far apart, so you can ignore that nearest neighbor distance. Okay, this is the way typically one solves any kind of diffusion in the dilute limit. Okay, so you put that, and now use the fact that in diffusion, distance square goes as r square goes as dt, and you put those two simple things together, and you find that in this case, your lambda should be 0 and z equals to 1. That Smoluchowski figured out by more rigorous calculation in 1960. But we do that in back of the envelope in a very simple scaling analysis. It's good to see that it matches. Now, when the system first become dense, a new length scale come in the problem, and that's the nearest neighbor distance, which did not exist before. And when that happens, then the diffusion velocity now can be written in terms of that instead of the one length scale Rg. You put it together and you find that lambda becomes larger than 0.2 and z is 1.25. So that's the intermediate phase where clusters are just becoming dense. And then at the later stage, when clusters are very large, cluster nearest neighbor distance is very small, they have no time to diffuse at all. They just go and hit someone. And we model that by the ballistic model. They're moving like in a straight line. So this is also computer simulation. Now we're coming to the morphology. You find that this is a very, very large system. We have what, 800,000 particle that we started out with. And you find that there is a morphology that gives you the fractal dimension of 1.8, and then a 2.6 for smaller q. Smaller q means q is inverse length, so larger clusters. And there is a crossover that related to the cluster size at the ideal gel point. So the ideal gel point that we can estimate from scaling another, that length scale, the size of the cluster at the ideal gel point, separates these two morphology. So you're getting a kind of a coherent picture of the clusters from dilute to dense, and then from a fractal dimension of 1.8 to 2.6. So here is our cartoon. This is what's going on, is that over this length scale, D is 1.8. This is more open. But these clusters of this size, they actually come together and form this super aggregate. And then over the larger length scale, they percolate. As you can see, this part percolates and then becomes super aggregates, and the fractal dimension is larger. So here is a colorful picture of that. So if you zoom in, okay, over shorter length scale, the fractal dimension is 1.8. That the people knew in the 70s and 80s. But those things, as the system becomes cluster dense, they come together and they form bigger and bigger cluster. And ultimately, if this is your system, the whole system will span, and you get into the percolation regime from there, and that's your fractal dimension of 2.6, which is known for percolation clusters. Okay, so, and what I just talked about once more, in the dense system, the morphology changes and the kinetics also changes. Here is random walk between finding another cluster. But when you are dense, then there is no room to diffuse. They pretty much go a little bit and find a neighbor. And that movement we call ballistic, and the kinetics is different for the two cases. So here is the summary. In the cluster dilute case, normal DLCA kinetics that people knew for 70s and 80s, and DF is 1.8. Now, you mean cluster dense, RNN comes into picture, and the enhanced kinetics comes in. Z becomes larger than 1, but the mean field model still works. Now you go to ideal gel point, where the nearest neighbor distance is about 2 times the size, that they're barely touching. That's your ideal gel point. And then super aggregates will form. And then physical final gel point. This is our model calculation. Aggregation happens beyond that. And then the single cluster will span the whole system. And in that length scale, you will find a percolation type fractal dimension. So all these things are written here with some things. Volume fraction 10 to the negative 4 to 3, and then it goes to the classical DLCA, then restricted free volume, where RNN becomes important, then pre-gel, ballistic, and then finally physical gel. And Smoluchevsky's mean field description works here, and it breaks down. So this graph gives you a physical picture of what I just talked about. Now, more surprises that beyond this. So this is your jello. So this is your very dilute. So what is it? If I remember correctly, the gelatin molecules volume fraction comes out to be about 0.3%. And so, but they come together, form fractal aggregates, spans the whole system and holds all the water in them. So this is very good low calorie food because all you are eating is the water. You know, okay, but you pay money to buy the water. They don't call it water. Yeah, that's the trick. Now, aerosol gel will form. One can estimate all these things. Any material should gel if the size of these monomers are less than 10 nanometer and the volume fraction is greater than 10 to the negative 4. So these are our scaling estimates. And here is a soot aerogel. So this came from Sorensen's lab, and this was actually marked by NASA as the lowest density solid material in the world. Because that's like jello, most of it is water. Here, most of it is air. But you don't call it air, you call it aerogel. You know, that's the way you market it. So we got a patent for that, for developing the world's lightest density material. And then Sorensen played with other things, and this is actually silica. So this is silica aerogel. You can create this thing just like in a suit. You can create this thing. Then, as I said, for many years, I was on the dark side. I was detached from that, and I missed out a big money-making opportunity. What was that? And again, it goes back to my mother and her kitchen. Turns out that this thing, this soot that Sorensen was creating at very high temperature by explosion, is nothing but graphene. So this is actually the cheapest way to make high quality bulk graphene. And if my mother only knew that this actually existed in her kitchen in 1960s, the history would have been different. So, so these are some TM thing. So what happened? Yeah, this is actually from a forest fire. They collected this soot from forest fire, and also has these two length scales, two different fractal dimensions that I was talking about. So with that knowledge that these things are graphene, very high quality graphene, Sorensen had another patent, but the first patent that we had, the low density gel, aerogel, and the second patent was kind of connected. So once that happened and showed that this is graphene, several companies got interested in working with Chris Sorensen to have a company. And then one company decided to come to Manhattan, Kansas, which is a very small town in middle of USA. And this company is called Hydrograph. So they worked with Chris, and they now started production of this graphene. See, and that's the patent that I was not part of. I was part of the first one, so I get a little bit of money for licensing from the first patent, but the big money is from the second. And the first money is very interesting. Well, I get some licensing money, but I don't know how to report that in my tax form. So I have to hire a tax accountant to put that, and he charged exactly the same amount of money that I got that year. So okay, you know, it's a push, as they say. All right. So I will end with a little bit of sidetrack, but this model. So Chris also designed a very simple model of these DLCA clusters. So he said, okay, how can this cluster aggregation happen? He said, all right, so you can have an end-to-end aggregation. So this particle and that particle come in here, and you can have one more. So you can form a chain. So that's your D equals to 1. Okay. You can do a side-to-side aggregation, and then you can create this kind of blocks which are D equals to 2, right? And the fractal dimension here is 1.8. So this is kind of in between the two. Okay, so that's side to end aggregation, and then it builds. So this is how it builds. This is in his model. This is actually in 2 dimensions. You can do this in 3 dimensions also, and then you create these successive Fibonacci numbers, and the limit becomes then 1.618, and you find that in 2 dimensions this will be, the fractal dimension is 1.4, which matches in 2-dimensional simulation. And in 3D also you can create this golden rectangle rather than the golden brick, and you put that together, and you can create this, you can create the fractal dimension that you will find to be 1.8. That's very good. This is a very nice, good model, matches fractal dimension. But we said, all right, now that you're making this golden brick in 3 dimensions, now there are 3 sides, and we should also look at the shape of it, meaning the ratio of the 2 sides, right? So we should look at that. So we did some simulations of that, and this is where statistical mechanics becomes beautiful. What happens in statistical mechanics, that the class that Rahul teaches or Thomas teaches you take, that there the most probable and the peak of the distribution, they're the same thing. So it matches that, right? The average value and the most probable value match. That's your statistical mechanics. So this is what happened in this case also. You get a distribution of these clusters, but look at the most probable value of these ratios, and this is exactly what this simple model of aggregation, the golden brick, if you will, promotes. So that becomes the most probable value of the shape ratios, and the complete distribution has a more wide probability distribution that's more complicated. So we are very happy to see that this matches with what the model that he was developing. And I think this is where I should end my talk and wait for some questions. But this is how growth happens in nature. This is from the classic book, the front picture, the classic book of Darcy Thompson's book on growth and form, how the snail, this is snail, it could be also in flowers, how this form develops. It shall widen and lengthen in the same unvarying proportions, the ratio of the 2 sides. And the simplest law is that which nature tends to follow: the shell grows in size but does not change its shape. So that's what coming out from all this discussion and all this simulation. Acknowledgement, of course, Chris Sorensen and many of my students, Dan Fry, Flint Pierce, William Heinzen, Justin Mon, and our own Thomas actually worked in the early part of this project many, many years ago. Thomas, do you remember? Yes. Say yes. All right. All right, so I'm going to stop here and answer any questions you might have. Thank you.
Thank you for this one today. No problem. Yeah. Are there any questions? I was thinking, what about the scales of these things?
Yeah.
We talk about the soot, which is micro scales, But can this structure form a much larger scale?
Yes, so
Let's
this is actually the
No, I'm thinking like galaxies or anything like. Does it follow some sort of similar?
oh, you're going to galaxies.
Yeah, it's sort of you probably have the filaments look very similar to what people have been looking the.
This one, look at
Uh-huh.
that one is what 5 centimeter or so. That is galaxy. Yeah, with the monomer size is nanometer. This is galaxy, right? Yeah, and this is where they found it to be graphene. This what they do is that they put a hydrocarbon gas, okay, acetylene or something like that, and then they use a way to ignite it. And at the flash point, the temperature is very close to 5,000 degrees Celsius when it happens. And at that point, then carbon kind of melts. It doesn't really melt, but it becomes more susceptible, and they form a crystalline structure. And that's what graphene is, a kind of a two-dimensional plate-like structure. And they tested that and found that it is. And it's a very cheap way to make bulk amount of graphene. You don't have to take a sellotape and take it out,
Just go
right?
to your mother's kitchen.
Yeah, or my mother's kitchen.
Collect your suit and.
Yeah. That's the bulk. That's the bulk. You can see the size is the size of this linear size of this thing about 5 centimeter, 4 centimeter, but it is three-dimensional. Yeah.
This is not like the supercritical drying stuff. No, this is not a solution.
You don't need any kind of supercritical drying. That's why it makes it so cheaper. Yeah, you take the gas, put in a cylinder, and ignite it, and the temperature, give a flash point, a flash at one point. The first experiment he was doing is that he has a metal cylinder, put the acetylene gas in it, and then get a spark plug from his car, tie it in and flash it, and it will ignite. And then, of course, then I was not the department head. Department head and all his crews came and safety violation. Okay. So he has to develop a more formal lab and all those things to build it. But it is a three-dimensional thing, very cheap to make. And so this is why this company is building a plant there to make this. And it's very high quality. Joan.
As far as I remember, the problem that you were having there is that when you were opening the high pressure pot,
Yeah.
was kind of fluffy, the material.
Yes.
So how you can manage to create this more solid stuff?
Okay, so that good question. So that depends on what gas you use as the atmosphere, and also at what pressure you use the gas that you put the hydrocarbon gas in with. And so he made various trials and errors, and then found something that mixed with it will create this kind of structure. Yeah.
Thanks.
Yeah. But yeah, you remember that early stage he was doing that. So this has been funded by funded by NASA. But NASA later told us that they have no interest in this kind of things anymore. I mean, we create
Recently or?
Well, define recently.
BT or AT?
No, this was several years ago.
Okay.
NASA, when NASA stopped experimenting on its flights, this is when they stopped all kind of research experiments. To do that, they just stopped that program completely. The space flights are not something they're doing. They kind of handed it over to private companies.
Any other questions? If not, let's thank Amit again.
Thank you. Thank you.